Good afternoon, welcome. My name is Simon Ritter. I'm the Deputy CTO of Azul Systems, and I'm going to be talking about Java at speed, building a better JVM. There will be time for questions at the end, so please hold those questions and then we'll deal with those at the end of the presentation rather than interrupting during the session. Okay, so what do we mean by speed in the Java world? What I'm going to talk about here is how we can improve the speed of the JVM itself, and not necessarily your application code. So I'm not talking about how you can reprogram your application to get faster performance. It's about how we can deliver better performance without you having to change anything, which is, the ideal kind of thing. And what I did was I thought to myself, okay, let's talk about how we can define performance. And I came up with a very interesting graph which shows the performance that we would really like in an ideal world for the JVM. And it looks like this, which is not a very exciting graph, I will admit, but it does show what we would like ideally. 100% performance all the way through running our application. So we start off, we get 100% of performance, run the application, and we stop. So that's what we really like. The problem is that if we look at the reality of a typical Java application, it looks very different. And what we see is a gradual sort of warm up of performance. We start off slow, gradually warm up and get to a sort of optimum level of performance. And the graph, as I say, looks very different. If we look at this in a little bit more detail, what we'll see is that when the application starts up, obviously, because it's Java, it's not compiled into native instructions. It's compiled into bytecodes, and those bytecodes are instructions for a virtual machine, hence Java virtual machine. Now, in order for those bytecodes to provide the instructions for the real machine, they need to be interpreted, converted from that virtual machine instructions to the real machine instructions. Now, often that's very simple translation, but in other situations, it's much more complicated and takes time and is inefficient from a performance point of view. So we see code being very slow to start off with. Now, one of the other things that we find is that the issue is that every time we see the same bytecode, we do the same thing with the Java virtual machine. There's no performance improvements in terms of caching or anything like that. So the way that we get around that is through just-in-time compilation, adaptive compilation. And how that works is that the JVM will count how many times individual methods are being used. And so when a particular method is called a certain number of times, it becomes a hotspot of code. And we need to then say, okay, let's improve that by compiling that code into native instructions, and then we don't have to do the interpreting every time. To do that, we use a JIT compiler that's called C1, used to be called the client JIT compiler, and it's designed to be a very fast compiler, generates code very quickly, but it doesn't do a lot of optimization. What it does do is also provide instructions that allow us to profile how that method is being used, and lots of information about that. So as we continue to run the application code and that method gets called more, we're collecting information about how the method is being used. Now, at the second level, second count of how many times the method is called, then the JVM will say, well, this is a really hot method. We need to then recompile that with more optimizations. So it uses a different JIT compiler called C2, used to be called the server compiler, and that will apply optimizations based on the profiling information that was collected during that C1 compiled code. We also get these things called deoptimizations, which are a result of what are called speculative optimizations being used to improve code. Speculative optimizations are basically where you make an assumption about how the code has run up to this point and say, well, if it has worked that way up until this point, let's assume it will work that way from now on. If you've got an if statement and you've only ever gone through the true branch, then you optimize based on that and avoid the false branch. Sometimes those optimizations and the speculative assertions are incorrect, so we need to throw away that code and then recompile it, and that's where you get deoptimizations. So eventually we will reach a steady optimized state. So that's our 100% of performance level that we would expect in terms of all the methods that are being used frequently are compiled with C2, with the profiling information and so on. But we still see some dips in performance, and those are due to something else. Those are due to garbage collection. Garbage collection introduces pauses depending on the algorithm you use. And so we see drops in performance whilst garbage collection work is happening. So what if there was a better way of having a JVM work? Well, that's what we've done at Azul. We've created this thing called Zing. Now, I don't want this to be a sales and marketing presentation. So what I'm going to do for the rest of the talk is explain how we actually make this work in a better way. What we did was we said, okay, the JVM is very good in terms of the code that it's using, and lots of it works really, really well. But there are certain areas that we think we can improve. And so we started from the idea of using OpenJDK, the open source code for Java, didn't start completely from scratch, didn't rewrite the whole thing. The important thing is, having made the changes that we do to the JVM, we still pass all of the TCK, JCK tests. And that's very important because it does make it a drop-in replacement for other JVMs, JDKs, such that you don't have to change any of your code to take advantage of Zing. You don't have to recompile any of your code to take advantage of Zing. What we have replaced is the garbage collectors. So all the garbage collectors are replaced with one which is called C4. I'm going to explain that in a moment. We've then replaced the C2 JIT compiler with one that we call Falcon. And again, I'll explain that. And then the last thing we've done is to add some technology to this, which is called ReadyNow. And that's designed to eliminate as much as possible this idea of the warm-up phase that you have to go through every time you start up your application. One thing to note about Zing is that because of the way that we do memory management, certainly in the past we've done some things with memory management, it's only supported on Linux. Technically, there's no reason we couldn't put it on Windows, but from an engineering perspective and resources, we've decided to focus purely on Linux. One of the reasons for being Linux only is a thing that we call Zing System Tools. And as I say, this enables us to provide better memory management for the JVM. Because if you look at Linux, Linux has a virtual memory system, maps physical pages of memory to virtual address space for applications. It's good, but it's designed for general purpose applications. In the case of the JVM, that's a very specific user of virtual memory. So we designed Zing System Tools to sit alongside the Linux virtual memory system and allow the Zing JVM to work in a more a high performance way for the way that memory is used. So it does things like returning memory to the kernel when it's no longer required. When we allocate new blocks, we can understand the cache status. We can make sure that where possible, we always allocate a hot block that's already in cache. And we can do some other clever tricks around things like what's called contingency memory that allows you actually to exceed the maximum heap size that you've set in order to prevent an out of memory exception, but then run the garbage collector more frequently to bring it back into line. Having said that, Zing System Tools, because that's a sort of an extra piece that you would need to install, if you're looking at microservices architectures and you want to deploy using things like Docker containers, then what we've now done is change the way that Zing works using some more modern Linux system calls, so that if you have a heap space of less than 1 terabyte, you don't need to use the Zing System Tools. You can if you want, but you don't have to. So you can deploy into containers as long as your heap space is less than 1 terabyte. Right, the way that we do garbage collection is different to the way that the other garbage collectors in Hotspot work. And we have this thing called C4, and it stands for the Continuous Concurrent Compacting Collector. And essentially, that tells you exactly what it does. It's a garbage collector that runs continuously in the background. It is fully concurrent, meaning that the application threads will run at the same time as all parts of garbage collection. And even though we do that, even though it is fully concurrent, we will compact the heap as we do garbage collection. And that's very important because we need to eliminate the fragmentation of the heap. We need to make sure that memory usage is contiguous where possible so that we can then allocate space in a more efficient way. From a basic point of view, we use similar approaches to many other algorithms. So first thing that we do is we use a generational heap space. We divide the heap space into 2 regions called young and old. Now, unlike a lot of other algorithms, we use the same algorithm on both of those. A lot of things, if you look at Hotspot, for example, and the way that it does the young generation, uses a very simple sort of pointer bumping algorithm. And then you can use things like CMS or G1 on the old generation. We use the same C4 algorithm on both. Now, the reason for that is more to do with making sure that we can minimize any pause times associated with how the system is working, rather than, and being more efficient, rather than having to worry about the way that the different algorithms work. Very important thing about C4 is all phases are parallel, meaning that if you have got multiple cores, then we can take advantage of that to make the algorithm more efficient by doing things at the same time with multiple cores. Also, very, very important about C4 is there is no stop the world compacting fallback. If you look at a lot of algorithms, so the parallel algorithm, the CMS algorithm, and G1, all of those will at some point, if the load on the collector reaches a certain level, there's too much fragmentation, it can't allocate fast enough, then it will do a stop the world pause, do a full compacting phase on the old generation, and that can lead to some very long pauses. You know, it could be seconds, could be minutes. Longest pause I've ever heard about was a day and a half. That's very extreme. Probably won't see that in many situations.
Eventuell, ich habe es bisher noch nicht probiert.
In terms of the algorithm that we use, it's a 3-phase algorithm. It's mark, relocate, and remap. Now, how does this work? Well, the most important thing about the algorithm is that we use a read barrier. So we use a loaded value barrier, is what we call it. And essentially, what that does is to enable us to have our collector run fully concurrently with application threads. We test object references every time they're loaded. And that means that every time you reference an object, we'll intercept that and test things to make sure that we know the state of the object header and how it's being used in terms of the garbage collection. That allows us to enforce 2 rules. So the first of those is that if we're in the marking phase, then every object that you are returned from the JVM will be marked to ensure that it won't be accidentally garbage collected. Second thing is, if we're in the relocation or remapping phase, then we will guarantee that you will get the right reference to the object, so that if you make changes to it, they won't be lost because we're in the process of moving the object and you update the wrong version of it. That won't happen. Now, a lot of people say, well, hang on, if you're intercepting the read to every object, surely that's going to degrade performance of the JVM. And the answer is, well, yes and no. Yes, it does, but it's not noticeable. It's negligible in terms of the impact. Reason for that is that the way we do things is by using some bits in the object header to determine what we need to do in terms of each object reference. We simply need to look at a bit in that header and we do a test and jump. If the bit is not in the state that we need it to be, we will jump to a handler. Most of the time, vast majority of the time, we don't need to do that. So we simply continue and return the reference. If you look at the underlying x86 architecture, a test and jump will boil down to a single micro operation, meaning the overhead of a reference is less than 1 nanosecond. And so if yes?
I'm sorry, could you just stop sharing the presentation for 1 second and then reshare it? Because some people have problems to see the shared screen.
Okay. Hang on. Okay, hopefully people can see it now.
Thank you. We'll see if it works.
Okay. Yes. So if you look at the impact of the test and jump compared to referencing L2 cache, L3 cache, or main memory, it's insignificant. How does this work then? Okay, so if we look at the overall algorithm, essentially what's going to happen is that we, again, follow similar ideas to other algorithms, starting off with what's called a root set. That's all the objects that you can access directly from your application code. So we scan the stack, we look at the registers, we look at the static variables, and we build up a list. Obviously, many of those references will have references to other objects, and so we need to trace the graph of object references through to make sure we identify all objects that are still being used. So the garbage collector will start working through the root set, and it will set the bit in the object header to indicate that this object is in use. And then it will follow the references and do that throughout the whole graph. Because the root set is independent objects, there's no contention, so we can do that in parallel. The application threads are running at the same time. And so we might get to a point where the application thread references an object, and we then need to go through our test and jump. We look at the object header bit and we see, it's not set. So at that point, we do jump to the handler. And in effect, we get a very small amount of the work of the garbage collector to be done in the context of the application thread. So we'll mark the bit to say it is in use, and then we'll allow the application to continue using that. Obviously, we need to trace any object references from there. We don't want to do that in terms of our handler. So we simply pass that object to the garbage collector and say, make it part of the root set and continue to follow the roots from there and work out all the objects that need to be marked. We then come to the relocation phase, where we need to move objects around within the heap in order to eliminate fragmentation and make them contiguous. So in the diagram here, we've got 5 objects, A, B, C, D, E. And to compact those, we need to copy each of those objects into a new position, which we can do by saying A prime, B prime, C prime, and so on. So we copy the objects from A to A prime and so on. In order to do that safely, we'll obviously put a lock around that. But in terms of pause times, that's negligible again, because most objects are very small. The time it takes to copy an individual object is very small, so your thread will not be blocked for any considerable period of time whilst that happens. So this allows us to compact the heap. Now, in terms of the new position of those objects, we record this information in a side table. So we'll say that A has moved to A prime, B has moved to B prime, and so on. What we then do is we go through a remapping phase. This is where we need to update the object headers to reflect the fact that we have moved the object from one place to another. And again, our garbage collection threads will do that by referencing the side table. They'll take the information about A, they'll update the information in the object header to reflect its new position, and then it will mark that to say that it has been updated. And then obviously we can do that in parallel because we don't have contention. Our application threads are running at the same time. So if the application references an object that hasn't been updated, hasn't been remapped, then again, we use our test and jump. We look at the bit is not in the state we need it to be. We jump to our handler. The handler will then take the information from the side table, update the reference, mark the bit to say that this work has now been done, and pass it back to the application thread. So now we have the correct position for our object guaranteed. This enables us to scale up to very big heaps. So big heaps for us are no problem. We can scale all the way up to 20 terabytes of heap without any degradation in pause times. Bigger your heap, you will not see increases in pause times. This is really good because it does mean you can use one big heap rather than trying to divide things into many small heaps to avoid garbage collection pauses or minimize them. One important thing to say is that although Zing does work very well with big heaps, it doesn't require a big heap. Let's talk a little bit about GC tuning, because this is something people spend a lot of time trying to get right. The reason for this is there are many, many options that you can use to change the way the garbage collectors work in Hotspot. And so people spend a lot of time doing that. And if we look at this example here, these are 2 real-world examples of command line flags that people have set up for a given application. And I don't want to go through all of the details of this, but what I will do is I'll just point out that both of these have set one particular value, the survivor ratio. One set it to 128, one set it to 2. Now, if you think about it, what's the right value? Is it 2? Is it 128? Is it 64? Is it 17? Probably not 17 because that's not an even number. But the point is that you don't know. And so it really comes down to trial and error as to what value makes the most sense for your application. If we only have one value to change, that wouldn't be too bad. But the problem is that there's lots of these values you can change, and you end up with an n-dimensional space trying to figure out the best set of options. If we look at the same thing for using Zing, it's a lot simpler. We simply set the heap size, maximum heap size, and then we let the algorithm underneath do all of the work, figure out how to make things work the way we want it to. Literally, the way that we start off in terms of tuning is simply to change the heap size, set it nice and big, gradually bring it down until you see that you're not getting the performance you need, and then increase it a bit to give yourself some overhead, and that's it. There are a few flags that can be set for different situations, but initial tuning, that's all you need to do. How can I prove that this works? Well, what we've done is to create a small open source tool called JHiccup. And this is designed to monitor and measure the latency of the JVM itself and everything below it. So nothing to do with your application. Doesn't matter what your application does. This is just about the latency of the JVM, the operating system, and the hardware. So to minimize any impact on the latency and the performance of the system itself, JHiccup spends most of its time asleep. So we put an extra thread alongside your application in the same JVM, doesn't interact with it, so there's no recoding or anything like that. And it goes to sleep for 1 millisecond. When it wakes up, it looks at the system clock using nanosecond resolution and says, I expected to wake up 1 millisecond later. I actually woke up 20 milliseconds later because there was a garbage collection pause, record that difference, and then we can generate histogram log files and we can graph them to show the results. And this is the kind of thing we see. So what we've done here is to take Elasticsearch with a reasonable size heap, 128 gigabytes, and run it on the exact same hardware, exact same load, exact same application. First time with Hotspot, second time with Zing. Now the graph that we're seeing here, if we look at the left-hand side of Hotspot, this shows latency of the JVM. And we can see a very typical graph where we've got lots of small spikes, which represent minor GC pauses. And we've got 2 big spikes, which represent major GC pauses. Remember, high spikes is bad. If we look at Zing on the right-hand side, remember this is exact same hardware, exact same application, you might think, well, hang on, big spikes is bad. You've got lots of big spikes, it's very random looking. But I've been deliberately misleading here because I've actually set the scale of the graph to be different. On the left-hand side, Hotspot is using 0 to 8 seconds. Zing on the right-hand side is using 0 to 80 milliseconds. If I change the scale of the graph to be the same, now you see the benefit of Zing. All of those garbage collection pauses that we were seeing with Hotspot have simply disappeared. And so you need to change the scale of the graph to actually understand, the level at which things are happening. Most of that you were seeing in the previous graph is down to the operating system, context switching, hardware, and so on. Smaller heap, 1 gigabyte Hazelcast system. And again, you can see without changing the scale of the graph here, that using Hotspot, we get a lot of garbage collection pauses. In fact, it's doing almost continuous garbage collection. And with Zing, we see basically flat line. So this really demonstrates the value of Zing in terms of GC. It just eliminates the problem of pauses. Next thing is the idea of JIT compilation. And so I mentioned that we've changed the way that the C2 JIT compiler works by replacing it with something we call Falcon. Now, Falcon is based on an open source project called LLVM. It's a project that's been around for a long time, lots of people contributing to it, people like Microsoft, NVIDIA, Intel, Sony, many engineers who understand about how to write compilers and how to use the hardware that's available. And so what we've done is we've taken that. It's primarily designed around static compilers and the sort of back end of code generation. We've taken that and we've integrated it into the JVM, make it work with the GC and the rest of the JVM infrastructure, and contributed that back to the project. This allows us to get much better performance in terms of better intrinsics. We can do more inlining of methods. We can have fewer compiler excludes, various things like that. So if we look at a simple code example, this is just a simple method that takes an array of integers and adds them up. Now, if you give that to any compiler, any modern compiler, that will be translated into the use of vector operations. Vector operations are where you have a very wide register, you load up many elements of your array, you can then apply a single operation to them in a single machine clock cycle, single instruction, multiple data. Been around for a long time. Very simple way of improving the efficiency of things like this. So that's good. Okay, so we can use vector operations for that and it doesn't matter. However, if we give a method that's slightly more complicated, we introduce the idea of a conditional, so we're only going to add things if something's even, then hand that to most compilers and they won't recognize that as something that can use vector operations. In the case of Falcon, it can. If we take that piece of code and we look at what hotspot and C2 will generate, we see this. Now, don't worry about all the individual things that are going on there in the instructions, but the key point here is that the only optimization that C2 is able to do is loop unrolling. And even then, it's only doing 2 elements per iteration of the loop. So it's very minimal improvement in terms of optimization. If we look at Falcon, although the code might look more complicated and bigger, what's happening here is that Falcon is analyzing that code and saying, we can actually use vector operations and the wide registers to do that. And so in the case of the specific machine we're using here, which is a Broadwell E5, we have AVX2 instructions available. So that's 256-bit wide registers. We can use that, load up a whole bunch of elements from our array, and if you look carefully there, you'll see that it's doing 4 elements loop unrolling. So we're actually doubling the number of loop unrolling elements in each iteration. And the overall effect of that is that for each iteration in the loop, Falcon code is doing 32 elements versus 2. And remember that because many of those are being done in parallel through the wide register, the overall improvement in performance is very significant. And that's where we can see, certainly in this particular case, for numerically intensive operations, that's a real improvement in performance. And that's just one example. LLVM is very modular, so we're able to work on other things. We're looking at more escape analysis, various things like that to improve performance even further now that we've integrated all the code and made everything work. Last thing to talk about is the idea of ReadyNow warm-up elimination. As I said, the problem we see is that it takes time to go from interpreted mode all the way through to our compiled code. The real problem is that we have to do that every time we start the application up. And that's, doesn't really help us at all, especially if we're doing something like microservices where we want to spin up new services very quickly. That's not really going to work very well. ReadyNow allows you to run an application, and then when you're happy with the performance, we record a profile. And the profile records 4 pieces of information. All the classes currently loaded, all the classes currently initialized, all the instruction profiling data that was generated from the C1 compiled code, and most importantly, any speculative optimizations that failed, meaning we had to throw away the code and then recompile it. By doing that, what we're able to do is when we start up the application again, using our ReadyNow profile, we can actually load all the classes that are possible to load, initialize all the classes we can initialize, and compile almost all the code before you actually get to your main entry point. So by the time you get to main and you start running your application code, you're running at about 98% of the performance you had when we took the profile. Literally, you need about 2 or 3 transactions to kind of kickstart everything to get back to that 100% level that you had before. Now, obviously, in terms of the amount of work that needs to be done before you get to your main, there's a lot more that's happening. And so to make that even better, we now do what's called compile stashing. So we now record also the idea of the code that was compiled in the previous run. And then if that fits and matches the profile that we've got, then we can reuse that without having to recompile it. The effect of ReadyNow is basically that, again, we see from a latency point of view, the orange line here is showing how we go through the sort of warm up where we start off slow with high latency, then we gradually compile, recompile before we get to our low latency. With ReadyNow, by using the profile, immediately start off with low latency because everything's compiled, everything works the way we want it to, and so you don't get this whole warm-up phase. Just to summarize then, the idea behind the Zing JVM is really to start fast. So it's the idea of eliminating this problem of warm-up by using ReadyNow, taking that profile, taking the cached code, reusing that so that when you start up your application, you don't have to go through interpreted mode, C1 compile code, Falcon compile code. You just go straight to Falcon compile code. Second thing is to go faster, because by using LLVM-based JIT compiler, we can get more optimizations. So the overall effect of the code is faster than we would have had if we were just using C2. And then the last thing, stay fast, is about eliminating the issue of garbage collection pauses as the application runs. Now, just one last thing I will say here is that some people say to me, well, hang on, if you're doing the garbage collection concurrently with the application threads, doesn't that reduce throughput? And yes, you would say, well, certainly it would, because you're doing more work concurrently, and that will reduce the amount of work that the application threads can do. But what we found is by using Falcon and improving the efficiency of the code we generate, we can compensate for that. So if you compare a hotspot running application to a Zing running application, you'll still get roughly the same throughput, but without all of those pauses. And so that's, again, a very important thing there. It is a very simple replacement, so you don't have to rewrite any of your code. You don't have to recompile any of your code. None of that's necessary. If you're interested in trying this out, you can go to our website, azul.com/Zing trial, and you can get a free license for 30 days. Try it on your machine. We will provide some help if you want, so that you can run JHiccup. You can produce graphs that show the latency of your application running on top of Hotspot, running on top of Zing, and then you can see the difference in terms of the performance there. So that's the end of the presentation part. So what I'll do now is I will throw this open to see if people have any questions. So let me just stop sharing my slides there. There we go. And then let's see, where are we? Need to find the chat. Okay. Right. Okay, so question here is, was the comparison for Zing versus Hotspot done with G1, garbage collector, or another one? Yes, I'm pretty sure that in the case of the graphs I showed you, that was definitely using G1, because we would have used the default garbage collector, which has been for a while now, is G1. So yes, certainly if you could have a look at CMS, but CMS has now been deprecated. In fact, it's been removed from JDK. So you would need to look at that, but you get very similar results with that. And is there any way or idea to use the compile stash in microservices and containers where it would spin up and throw away pods regularly? Yes, absolutely. I mean, this is one of the advantages of doing that, you see, because you can create a compile stash and a profile for a microservice, so that when you want to start up that microservice quickly, you can put the profile and the compile stash into the container, make it part of the image, and then when you start up that particular service, we can make use of that straight away and get much faster startup in terms of the actual service that you're actually creating. And that's one of the things. Obviously, if you look at Zing, it helps in terms of the startup time. Other people have different approaches to this. So if you look at things like LLVM, Quarkus, that's about getting very fast startup through native compilation and ahead of time compilation. What you get with Zing is the benefit of that fast startup, but also much better performing code, because JIT compiled code will generate much better performance than you'll get with ahead of time compilation, because of the issues of things like not being able to do as aggressive method inlining, and the use of speculative optimizations is much more restricted in terms of ahead of time compilation, even with profile guided optimization. Okay, I've got another question here. Is there a way it would be useful to get the profiling info from a production system after a while to build it into the next container? Yes, again, that's absolutely how the whole ReadyNow system is designed to work, is that you run it on a production system, you generate a profile, and then you can deploy it into a container and put it on whichever machines you want to deploy it onto. So you make it part of the image, and then you get the benefits of that. So yes, that's certainly from a microservice point of view, that's one of the real benefits of doing this, is that you can put the whole profile and compile stash inside the container. Okay, so since I'm not seeing any more questions, I think I will wrap up the session here, and I'll say thank you very much for listening.